we are going to work through some challenge problems involving projectile motion. So we'll start on these challenge problems we were given. We're going to work backwards, starting with 6, moving our way to number 5. Okay, a person throws a dart at 15 meters per second along an angle of 18 degrees. The dart is thrown from a height of 1 meter off the ground. All right, in that case, what we're looking at is, here is the dart thrown from an initial height of 1 meter, and the dart is launched at this angle. The initial velocity is 15 meters per second. Of course, that means the dart is moving horizontally and also vertically at the beginning. The vertical velocity changes, so I'm going to add initial here along with y. The horizontal velocity does not change, it stays fixed because gravity does not pull left or right, only up or down. Okay, let's try that again, Vx. All right, the dart is thrown. Okay, we could go ahead at this point because we know this is 18. We could go ahead and find VIY and Vx. Will this be useful? I have no idea, but worth a shot, right? So the y component is opposite the angle, and so we do hypotenuse sine theta. The x component is adjacent the angle, so we do hypotenuse cosine theta. Okay, I'm not going to calculate that yet, just yet, but I want to keep reading. The dartboard is located 4 meters away from the person. The top of the board is 1.5 meters off the ground, and the bottom is 1.2 meters off the ground. Determine whether the dart hits the board. So this dart is going to travel to the right. How far? 4 meters is equal to delta x. Whoops, I don't have enough zeros there. That's okay. I'm not really worrying too much about sig figs just yet. And okay, so the question is that there's like a board, you know, that goes from 1.2 to 1.5. I'm not going to write those into my diagram because they're right there in the text. 1.2 and 1.5, right? But what I want to say is, how am I going to solve this? What I would like to do is find the delta y of the dart. Maybe the dart does this. Maybe the dart does this. Maybe the dart hits, right? Who knows? The point is, if I find how far, as the dart travels to the right, if I find how far up it goes, if I find the dart's delta y, I can compare the final height of the dart to these values, 1.5 and 1.2, and then I can check to see whether the dart hits the board. That's my method. Find delta y, then final position, and compare. Okay. So how do I find delta y? Well, you can look at what we've been given. You can probably deduce that we're going to need the x-axis first. We know Vx, it's this. We know delta x, it's 4 meters. So we can solve for time. So Vx, okay, if I write this equation again, but rearrange, I'm going to multiply both sides by t, then divide both sides by Vx. And so I have delta x on top, that's 4. And on the bottom I have Vx, which is 15 cosine 18. So I turn on my calculator, I do the calculation. Take note, I will get the wrong answer if I just do this. And the reason is because the calculator is taking 4/15 multiplied by cosine of 18. We want the cosine to be part of the denominator, and so we have to use parentheses if you do it all in one step. So see how this gives me the wrong answer? See that? That's different, that's wrong. Okay, so what's my time? 0.2803 ... Now that I know time, let's turn to the y-axis. Which y-axis equation has VIY, the acceleration due to gravity, time I know, and I'm looking for delta y? The equation we need is this one, of course. Plug in the values and solve for delta y. So VI, I'm going to plug that in. That is 15 sine theta. That's what I said right here. Time was 0.28 ... Keep those digits. Plug in the time right here. And when we calculate, this comes to about 0.9. I'm getting fancy with my calculator work here. Check this out. I redid that calculation for time, and then instead of typing 0.28039 or whatever, I'm just doing second answer. Let me delete that. And I can even square the answer. Here's minus 4.905, and then multiplied by second answer squared. If you want to second insert a star to multiply, you can do it this way. You'll get the same thing. And what's this? I made a mistake. I had 8, not 18. Careful, I can't just re-enter the whole calculation because now the answer is referring to the 0.19, which is not the time. So let me second enter once more and then pull up that calculation I was hoping to do. Second insert a 1 and then hit enter. 0.914. So what is the final height of the dart? Well, oops. The dart started at, okay, delta y is equal to final minus initial. Delta y was 0.9. You'll see why I'm leaving off the extra digits. Its final height is what we're looking for. The initial height was 1 meter. When we add 1 to both sides, we get 1.9 meters. And those extra places won't make any difference. We can see right away the dart does not hit the target. It doesn't hit the board. It goes way too high. The top of the board is at 1.5 meters off the ground, and the dart lands all the way up here at 1.9. All right, on to the next problem, number 5. Okay, in this one we have a monkey standing on the ground. Kind of looks like a person. Here we go, here's some ears, and there's its tail. And it sees a tree that is has a banana, which is about to fall. I have no idea if bananas actually grow on trees. Let's say yes, they do. I know they do. I know that because of Jungle Book. Okay, so she sees the tree, she sees the banana is about to fall from rest. The tree is 4 meters to the right, and the banana is 6 meters up. My picture is horribly inaccurate. That's okay. 6 meters should be taller, but c'est la vie. All right. In the instant the banana falls from rest, maybe it should say, the monkey starts to jump at an angle theta toward the banana. All right, so then let's see. Let's draw that into the picture. So the monkey, you can treat it as being on the ground. It has some initial velocity, and there's some angle theta, and it is jumping. So by jumping along this angle, it has some initial y velocity and some x velocity. The y velocity, I put the initial because that velocity changes. Gravity slows it down and then speeds it up. The x velocity, I don't need an I because it never changes. Okay. In the instant the banana falls, so the banana falls from rest. And oh, look at this. I've got 2 objects. I better have separate groupings for their given information. Of course, the banana also is in free fall. And in the second that it falls from rest, the monkey jumps. And the monkey catches the banana, but we must find the angle. Find theta. This is a great one. So we are first going to look at the two objects, because whenever we have two objects, we look for quantities that are the same. Well, if they meet midair, maybe right here, then their final y position is the same, and so is the time that they've both been in the air. So let's write that down. Same y final and time. It's supposed to be an exclamation mark. Okay. Well, let's write down a y-axis equation since they have the same y final. All right, well, for the monkey, we could use, let's just try the same one that we tend to use. This one. Of course, delta y is final position minus initial position, which for the monkey is 0. So let me just write y final then. I'll show the whole thing. The monkey's initial velocity is just, on the y-axis, is just the total velocity, sine theta, multiplied by time, and then plus 1/2 ag t squared. That's about as far as we could get. We could plug in ag, the acceleration due to gravity, but it's not really going to get us any farther. So let's just pause there and turn to the banana. This is the monkey. Monkey. Okay, now time for the banana. The banana, we could even write the exact same equation. The banana's final position minus its initial position, which is 6 meters off the ground, is equal to its initial velocity multiplied by time plus 1/2 acceleration times time squared. But the banana falls from rest, and so the initial velocity is 0. 0 multiplied by time is 0. And so for the banana, we have just this. I'm showing my work along the way and then erasing, but you would want to show all of these steps. Look what happens. Maybe I'll show this. If you isolate y final, add 6 to both sides, now we have two expressions. This is equal to y final and this. And guess what? It's the same y final we said. So equate this with this, and let's see what happens. Maybe we'll get somewhere. All right, when we equate those, we have, okay, vi sine theta multiplied by time plus 1/2 a t squared is equal to 6. Now I'm getting this one. Plus 1/2 a t squared. And look at what happens. You can subtract 1/2 a t squared from both sides, and that terrible term just goes away. And now, what do we have? Vi sine theta multiplied by time is equal to 6. That's much simpler. But we still have 3 unknowns. So how can we get, whenever you have that many unknowns, we're going to need more equations. How can we find more equations? Well, we haven't used the x-axis or this fact yet, so let's utilize that information. The monkey's x motion is constant. There is constant velocity because gravity doesn't pull the monkey left or right, only up or down. But the x velocity is also equal to vi cosine theta, because this is the adjacent leg of the triangle, hypotenuse cos theta. And, if we'll look at this. If we plug in as delta x 4 meters, I don't need that Vx anymore. I have the exact same 3 givens. pardon me, I have the exact same unknowns, time, vi, and theta, here as I have here. So if I said earlier that the time was the same for both. So if I isolate t, and then do the same, or maybe now let's just substitute that in for t here. Let's see what we get. Okay, so I go vi times sine theta times 4 over vi cos theta is equal to 6. And look at how this simplifies. The vi divided by vi cancels out. Moreover, let me move this up. Moreover, what we have now is sine of theta divided by cosine, and that, believe it or not, is equal to tangent of theta. So tangent of theta times 4 equals 6. If you divide both sides by 4, you get tangent of theta equals 3/2, or 1.5. And theta then is inverse tan of 3/2. And if you plug that into the calculator, second tan, 3/2, whoa, 56 degrees. Of course, I need 3 sig figs. That's what the givens have, so 56.3, which is pretty cool. If you don't believe me that sine over cosine is equal to tangent, check this out. Sine over cosine. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. But you can see the hypotenuse will cancel. We are left with opposite over adjacent, which is tangent of theta. Part B. It says, assume the monkey catches the banana in the final moment just before it hits the ground. Thankfully, don't have to worry about the 5-second rule. So, okay, the banana is at the ground, the monkey is at the ground. We've just been told y final is 0. Calculate vi. So look back to the equations and see if it helps to plug y final equal to 0 into any of those equations from the previous part. All right, well, where's the first place we see y final? Here's one spot. We have vi, theta, and t. Let's look down to the next equation. If I make this 0, my only unknown is time, because I know this is negative 9.81. So let's start with that equation. Y final is now 0 minus 6. Well, hang on. Negative 9.81 times a half is 4.905. And if you... Okay, so we can get rid of the 0 minus 6 is just negative 6. 0 minus the blah is the blah, just negative. And so now we can divide both sides by negative 4.905. This will cancel. We will square root both sides, and t will be see how the negatives will cancel? 1.106. Finally, we're looking for vi, so let's use that equation up above, the one that I skipped over. Or use this equation. Either one will give it to you. Or let's see, this one if you like. This one up here. Any equation with vi now can be used. I'll use that one up above. That looks simpler. So 4 over my time is equal to VI times cosine of, what was theta? Oh yeah, 56.3099. Ideally, you keep all of the extra decimal places until the very end. And so what do we get over here? We have 4 over 1 point, no, let me do 4 over second answer. And then I also need to take the 4 and divide it by cosine of 56.3099. That's good enough. 6.52. How many sig figs? We want, dun, 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 3 siggy figgies. There it is. Onward and upward, or we're going backward, so is it downward and upward? I don't know. All right, number 4. Calvin and Hobbes are riding on a sled. They're trying to jump the gap between 2 symmetrical ramps of snow separated by a distance of 8 meters. Why do they give it all these different letters and names? This is not W, this is delta x, the forward displacement. Each ramp makes an angle of 35 degrees. They launch off the first ramp with a speed VL. Again, why is that VL? Can't we just call that VI? I don't know. What value of the initial launch speed results in the sled landing exactly at the peak of the second ramp? So in other words, it's not doing this. You're not doing this. You are landing exactly at the peak, like this. And so here's the sled at the other side. And we have to find VI, which makes this, what we've drawn, true. The key here is to realize that if you start and end at the same level, then your delta y is 0. Okay, so let's write down some equations, right? Because that's how we move forward. We write equations. And if we don't have, if there are too many unknowns, we write more equations, and then we solve the equations. On the x-axis, Vx is, of course, delta x over time. Vx, though, I can say is Vi times cosine, right? Your angle here is the same. This is 35. The x-axis velocity is adjacent, so we use cosine. Delta x is 8. And that's all we can do. We have 2 unknowns. All right, if we have 2 unknowns, we need 2 equations to solve for those unknowns. So let's turn to the y-axis. We know delta y. We know VIY is VI sine theta. We know, what else do we know? We know it's the same t here as here. And we also know, acceleration due to gravity. So which equation has those 4 things? It's the same one we always end up using. This one. So let's plug in delta y is 0. VIY is just the whole velocity initial times sine of theta times t minus 4.905, right? Half of 9.81, but it's negative t squared. Well, let's keep going because we could simplify this. Let's add 4.905 to both sides. 4.905 multiplied by t squared. This is all a single term, so you have to add the whole thing to the other side. And on the right, we are left with just this. This is all that's left, because this went over, became 0. If you divide, wait, we have a t on both sides. Divide both sides by t. This one cancels entirely, and this cancels one of the t's. So now we have 4.905 t equals VI sine theta. And look at this. If we, I don't know, isolate t, let's isolate this t. I'm being crafty. I multiply both sides by t, then I divide both sides by that. Got to get t out of the denominator. And then if I plug this t in, this expression for t, right, the time is equal to what I just solved for. What happens? Well, 4.905 times 8 over VI cos 35. I guess it didn't actually matter how I did this. Equals VI sine 35. Theta is 35. If you multiply both sides by VI, this one cancels, and then you end up with VI squared. Then you can divide both sides by sine 35. And then you're going to need, that cancels. But of course, VI is squared, so to finally isolate it, we need to square root both sides. So what did we do here? We came up with two equations, and then we solved the system of two equations. All right, so square root 4.905. I'm guessing the negative is going to cancel. Oh yeah, I added it, so that made it go away. I've got to multiply by 8. I need to divide by sine of 35. And then I'm also taking the answer to that and dividing it by cosine of 35. 9.13 is my answer. How many sig figs? 35 had 2. So my answer is 9.1 meters per second. Wow. Number 3. All right, I will assume you have read the question. Notice that at the peak height where we are here, the final y velocity is 0. Let me try to write that again. At the peak height, the final y velocity is 0. Okay, so delta x is this what they've called d, which is 5 meters. Delta y is 2.5. And VFY is 0. Of course, on the y-axis, we know the acceleration due to gravity. And we are looking for the angle theta. Again, just start writing equations down. The x velocity is displacement over time. We use the equation for constant velocity on the x-axis because this x velocity doesn't change. Don't use an equation with VI or VF. It's a constant velocity on the x-axis. Gravity doesn't pull up or down. Sorry, it doesn't pull left or right. So, in place of Vx, I could say Vi cosine theta. Because the Vx is always the adjacent leg, adjacent to the angle. And okay, is there anything else I can say? Yeah, delta x, I know the value, it's 5. Okay. That's the end of my progress. I have right now 3 unknowns, Vi, theta, and time. So I will need more equations. All right, on the y-axis. We know delta y, we know Ag. We know it's the same time to go up as it is to go over. Same time as here. So maybe I should find an equation with time. And I also know, what else do I know? Well, I know VIY is VI sine theta. And that's the same theta here as here. It's the same VI as here. All right, which equation has these 4 things? Delta y, Ag, T, VIY. It's this one. And if you plug in delta y is 2.5, the initial y, oh, hang on. The final y velocity is 0. Maybe I should use an equation that has that. That's extra information. If I go with this equation, I'm going to end up with 3 unknowns, Vi, theta, and time. So let me try a different equation and see if that helps. See if I can make any progress using an equation that has the extra information. If you have information, use it, right? All right, so then what should I try? Maybe I'm just a guess. I'll try this one. Delta y was 2.5. VIY is just VI sine theta. When I add VF, I'm adding 0, and so that doesn't change the parentheses, what's inside. If I multiply both sides by 2, 2.5 multiplied by 2 is 5. And look at this. It's the same time here as here. So let's isolate t, and then substitute our expression. Whatever we get here, we're going to plug it in for t right there. When I isolate t, I divide by what's in parentheses. And if I plug that in, VI cos theta, 5 over VI sine theta. Whoa, hang on, what happened? T is here. T is 5 over VI sine theta. All right, that's better. If you like, instead of taking 5 and dividing by this mess, take 5 and multiply by the reciprocal. And we see the 5 cancels. The VI even cancels. We have cosine theta equals sine theta. Now, before I write cosine theta equals sine theta, I could leave the VI in and look at what we've got. VI is such that the x component is equal to the y component. What triangle, there's only one, what triangle has the two legs equal? A 45, 45, 90 triangle. So we immediately can say theta is 45. Now it is possible to solve for this. If you cancel VI, then divide both sides by cosine of theta. Cosine of theta divided by cosine of theta is the left. That's going to turn into 1. This, of course, is 1. Sine over cosine, that's the trick we learned earlier, is equal to tangent. So theta is equal to the inverse tangent of 1. And guess what that gives us? Second tan of 1, 45 degrees. Next up is number 2. A person at rest throws a ball upwards at some initial speed of 4 meters per second. Okay. Go up. So this is 4. The hypotenuse is 4. The angle is 25. Okay, 25. And of course, this means there is some x velocity to the ball. The x velocity of the ball doesn't change. There's also a y velocity initial, which does change because of gravity. All right. Let's see. Immediately upon throwing the ball, she tries to catch up to it by accelerating from rest. Ooh, from rest. Her VI is 0. With a constant acceleration for a time t. She catches the ball at exactly the same height as she threw it. What is her acceleration? If you don't have the instinct, here's how you need to start. Whenever you have two objects, separate the givens. Otherwise, if you don't separate the givens, you'll end up saying like, oh, VI is 4. You'll end up saying, oh, why is this not working? You'll say something like, VI is 4, right? It says so right there. But then you'll say from rest, VI is also 0. And you'll be like, which one is which? Why is it both? It's not both. The ball has VI of 4, theta of 25. The person has VI of 0. Different objects. Of course, the ball accelerates due to gravity along the y-axis. It does not accelerate on the x-axis If I wanted, I could call this a sub y. But I like g. I remember when I write ag, I know that that's the y-axis only. The ball is in the air for some time. It moves forward. And whenever you have two objects, you look for equal quantities. That's the trick. In this case, what two quantities are equal for both person and ball? The ball has the same delta x because they land together as the person. And the person also has the same time because she catches up to the ball in the same time that it's in the air. Now, the only thing I've missed, if the ball starts and ends at the same spot, what do we know? Delta y is 0. So here's our method. The person accelerates. We know we need to use one of these equations for the person. Her acceleration is not 9.81 because she's not in free fall. She's on the ground. Just the ball is in free fall. So we're going to need one of these equations. Which one, I don't yet know. There's also vf squared equals vi squared plus 2a delta y. Oops, delta x, she moves on the x-axis, pardon me. And the final one is vf minus vi over time. Okay, so once we find delta x and t, we can solve for her acceleration. So find those. How do we find those? You may not be surprised to know that, whoops, what happened? The ball, of course, has its x motion and its y motion. We separate the two. So the ball's x velocity is constant. Therefore, we use the simpler equation, just displacement divided by time. But of course, the x velocity is vi cosine theta. Hypotenuse sine theta for adjacent. Delta x, I don't know. But what do I know? I know vi, I know theta. I don't know time, all right? Let me turn to the y motion first. On the y-axis, I always use this equation, right? vi, y, t. Let's write it down and see if it gets us anywhere. You can be more disciplined. You can look at, oh, I've got delta y, I've got vi, y, I've got ag, I'm looking for time. So delta y is 0. The initial velocity is, on the y-axis, is 4 sine 25 multiplied by time. Whoa. Half of ag is negative 4.905 t squared. Add the 4.905 t squared to both sides. Then you can divide both sides by a t. That cancels one of the t's. And then you just have to divide both sides by 4.905. So 4 sine 25 over 4.905. 0.3446428. All right, I found time. That was one of my objectives. Why? Because now I know her t. Her t. 3446. If I can find her delta x, I can solve for acceleration. How do I find her delta x? Oh, I use the time and I plug it right there. I'm going to cross multiply, so what's that going to be? I should show my work. That's what you have to do. Vi is 4 times cosine of, what's theta? 25. Multiplied by t was 0.3. You got to show this, even though you could just plug straight to the calculator. Show this work. Watch this. Second enter. And then I change that from sine to cosine. I don't know if this actually saves me any time. Second answer. delete, 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 delete. 1.25. 249. 1.49 ... meters. And I could put that down here. Probably would be good of me to say 1.249. Yes, I know what's up. I got the answer. And then I look at the person and I say, hey, I know her delta x. I know, I know her time. I know VI, 0. VI, and I know her acceleration. It's not AG. She's not in free fall. Hang on. That's a mistake. Okay, I know her, I don't know her acceleration. I'm looking for acceleration. The final thing I know is, well, no, that's it. So which equation has 3 givens and 1 unknown? The first one. Delta x is equal to VI times t, but VI is 0. So this whole thing is all 0. 0 multiplied by time is 0. That makes life a little easier. Don't use negative 9.81. We don't know how fast she accelerates. She's not falling down. She's going to the right. What's t? 0.3446 ... squared. So we will need to multiply by 2, divide by 0.3446 squared. And what's that going to give us? I take my answer, times it by 2, divide it by 0.3446. Should I do one more digit? And I hit enter. Her acceleration is 21 meters per second squared. Quite fast. That's what she would have to do. Maybe it's not possible. Maybe she can't accelerate past 10 meters per second squared or something. That would be a nice way to ask the question. Maybe I would say she can accelerate at a maximum value of 10 meters per second squared. Does she catch the ball? And then you would do the exact same thing. You would compare to her actual achievable acceleration. And you would say, no, this is not big enough. She can't make it all the way up to 21. So she doesn't catch the ball. That would be a nice way to make this question a little bit harder. Number 1, the only thing I'm going to let you solve B and C because those are really straightforward. Here you just find how long, that's the time. Here you found how far, which really is forward, because launch and landing heights are the same. That means delta y is 0. Whoa. So if it goes like this, the total displacement on the y-axis, you know, it starts right here on the y-axis and it ends right there on the y-axis. No y displacement. Yeah, so you don't find delta y, pardon me, moving too quickly. You were looking for how far forward, really. You were looking for delta x. But let's just quickly peek at number 1, part A. Okay, a rock is thrown with an initial velocity, vertical velocity component, hey, of 30 meters per second, and an initial horizontal velocity component of 40. They have given me not VI and theta, they gave me Vx and VIY. I don't have to use sine or cosine. They actually gave me the components. I mean, in fact, if you wanted VI, you could do 30 squared plus 40 squared. The hypotenuse would come to 50. I could calculate VI if I wanted. I don't want to because I don't have to. So let's take that away. All right, the question, what will these velocity components be 1 second after the rock reaches the top of its path? Here is what I want to point out. If we just assume it's launched from the ground, they don't tell us, so it doesn't really matter how we draw the picture. The point here is that the rock goes up and comes back down to the ground. They gave us these velocities, but they're telling us consider from the very peak until, this is now the initial, until 1 second later, when it's maybe here, I don't know, somewhere on the downward path. Consider from that initial to that final. And what is VIY at the peak? It's 0, we learned. So we will not use 40 as VIY. That 40 refers to a different initial moment, this moment, which is really not what they asked us to consider in this question. They asked us to consider the peak as the initial moment. So what you have to do is let VIY be 0. VIY is 0, not the 40. The time that occurs, the time that passes is 1 second. And we know AG. We seek the velocity final on the y-axis. And the equation that you can use, I'm rearranging this. I'll let you do this work. There it is. This is 0. This is 1. 1 times negative 9.81 is just negative 9.81 meters per second. We would round that to 10 because the siggy figgies are pretty slim. Just 1 sig fig for both of those values. That's the y velocity 1 second after being at the peak. What's the x velocity 1 second later? It's always 30. It never changes because there is no acceleration on the x-axis. Gravity doesn't pull left or right, it only pulls down. And that concludes this video. Congrats if you made it through the entire 47 minutes. I'm a little surprised I did.